Every microchip inside your phone or computer is essentially a nanoscopic city. It's built on billions of microscopic transistors that act as the ones and zeros of our digital world. For 50 years, the tech industry relied on a steady rhythm called Moore's Law. Every 2 years, engineers figured out how to shrink those transistors, packing twice as much computing power into the exact same physical space. To build something that small, you can't use physical tools. You have to use light. This diagram shows the standard process of photolithography. Engineers design a pattern stencil, and by shining a light wave through those gaps, they project a microscopic blueprint onto the silicon wafer below. But around 2015, that shrinking process hit a hard physical limit. As you can see here, when engineers tried to make the gaps in the stencil smaller than the wavelength of the light itself, the physics broke down. The waves diffracted. They started bending and overlapping into a blurry, undefined mess. You couldn't print a crisp transistor anymore. The only theoretical way past this barrier was to use a completely different kind of light, specifically extreme ultraviolet, or EUV light, which has a wavelength of just 13.5 nanometers. Harnessing a wave that tiny required a machine that didn't exist, using physics that nobody had ever tested. The engineering hurdles were so steep that almost every major tech player looked at the blueprints and walked away. The entire industry effectively gave up. That left exactly one stubborn company in the Netherlands, ASML, willing to try and build it. To keep the global digital economy from stalling out, this single team embarked on a 3-decade project. They had to systematically outsmart the laws of physics, one impossible problem at a time. The first major hurdle was the light itself. EUV light is basically weak X-ray radiation. It carries so much energy that it acts completely differently than visible light. In this simulation, you can see what happens when EUV hits a standard glass lens. Instead of passing through to be focused, the light is immediately absorbed by the atoms in the glass and dissipates. Since they couldn't shoot light through a lens, engineers had to redesign the optics. Looking at this diagram, the solution was to use a series of highly polished, curved mirrors to catch the light and bounce it toward a precise focal point. There was just one massive complication. EUV light gets absorbed by mirrors too. To fix this, we have to look closely at the surface of the mirror itself. By stacking dozens of nanometer-thin layers of alternating silicon and molybdenum, the light waves hit the boundaries, flip their phase, and perfectly align their peaks to bounce back out through constructive interference. That atomic stacking trick worked, but it created an entirely new crisis. The light has to bounce off multiple mirrors to finally reach the silicon wafer. Even with perfect engineering, each mirror absorbs a tiny percentage of the energy. By the time it reaches the end of the line, over 90% of the light is gone. To have enough energy left to print a chip, the initial light source had to be impossibly, destructively bright. Finding a light source that intense meant stepping completely outside traditional electronics. The search led to the Lawrence Livermore National Lab in California, a heavily funded facility dedicated to designing nuclear weapons. Scientists here spent decades analyzing the extreme X-ray radiation released during nuclear fusion. To generate the specific EUV light ASML needed, they essentially had to build a controlled, continuous artificial sun right inside a laboratory. The mechanism they eventually invented is pure chaos. Take a look at this extreme slow-motion render. A microscopic droplet of molten tin is shot out of a nozzle, falling through a pitch-black vacuum chamber. As you can see in this animation, the droplet doesn't just fall. It is intercepted by a high-powered industrial laser. This first laser pulse acts like a hammer. It smacks the tin from the side, instantly flattening the perfect sphere into a much wider oval, expanding its surface area. A split second later, a second, massively powerful laser slams into that flattened target. It vaporizes the tin entirely, ripping away its electrons and creating a plasma cloud over 220,000 degrees Celsius. That exact explosion is what finally emits the 13.5 nanometer light. For this system to generate enough continuous power, that perfect two-step laser strike can't just happen once. It has to happen 50,000 times every single second. So they successfully created a continuous micro-supernova. But setting off 50,000 explosions a second inside a machine triggers a fatal consequence. All that vaporized tin instantly blasts outward, guaranteeing it will coat and destroy the million-dollar atomically perfect mirror sitting just inches away. The inside of this chamber is a violent, hostile environment. Every plasma explosion sends a rapid shockwave tearing through the dark space, carrying tiny fragments of molten metal with it. To protect the delicate optics, engineers deployed an invisible shield. As shown in this diagram, they pump low-pressure hydrogen gas through the chamber at hurricane speeds. This rapid crossbreeze physically catches the metallic debris and sweeps it away before it ever touches the glass. But we're not done breaking physics yet. Blasting hurricane force gas over a mirror that is sitting next to a 220,000-degree plasma fire creates immense heat and friction. The mirrors physically warp and shift from the thermal stress, throwing the bouncing light beam completely off target. So, the optics manufacturer Zeiss built a robotic nervous system directly into the hardware. You can see the concept mapped out here. An array of sensors continuously monitors the exact position of every mirror, dynamically tilting and micro-adjusting the angles in real time to counteract the heat distortion. The required accuracy is measured in picoradians. To put that in perspective, the physical adjustments happening to these mirrors are the equivalent of standing on Earth, aiming a laser pointer into the night sky, and successfully hitting a single dime resting on the surface of the moon. Look at the cascade of problems they solved. They bypassed the optics limit with atomic scale layers. They fixed the power deficit by detonating 50,000 micro-supernovas a second. And they prevented the machine from destroying itself by combining hurricane force gas with lunar-level robotic aiming. The final working product is a beast of mechanical engineering. Inside the clean room, heavy metallic track systems whip the silicon wafers back and forth at over 20 Gs of acceleration. That is 5 times the G-force of a Formula One car, all to print layers of a microchip with a maximum error margin of just 5 atoms. The logistical footprint is massive. A single completed machine costs upwards of $400 million and requires 3,000 cables, 40,000 bolts, and 7 Boeing 747 cargo planes just to ship the parts across the globe. This victory required immense financial faith. When the research hit roadblocks, desperate tech giants like Intel, Samsung, and TSMC poured billions of dollars into the project. They were effectively betting their entire corporate survival on an unproven concept. And for decades, the doubt was deafening. The earliest pioneers of this extreme ultraviolet technology were literally laughed off the stage at conferences by the greatest experts of their era. The traditional scientific establishment viewed the entire endeavor as a joke. The foundation of this multi-billion-dollar industry didn't start in a pristine corporate boardroom. It started with a handful of isolated scientists, sitting at desks over their Christmas holidays, stubbornly writing theoretical white papers, purely out of spite. Without them, Moore's Law would have died a decade ago, taking the exponential growth of the tech industry down with it. Instead, this single, impossibly complex machine dragged the global digital economy into the future. We often assume that the miraculous technology powering our daily lives just arrives through the natural, inevitable march of science. But it doesn't. It exists almost entirely because a few unreasonable people refused to accept the strict limits of physics and completely ignored the ridicule of their peers.